Okay, so the first written assignment, I think I released the grades earlier today. And for the most part, it was all straightforward. There were a couple of little glitches here and there. Check the comments for anything about that, and if there are any issues, concerns, see me. Be happy to talk about that. And we will now move on to what is going on for today. So let's see if this will work this time. Okay, it's not showing that. That's not what I wanted to share. Out loud. Okay, well, except I can't see it. Can't I see it? All right. All right, can everybody see the slides now? Okay, there they are. Hopefully by the end of the quarter, I will have figured out what it is doing with this, because it's offering me two things to click on, and I guessed wrong this time. Okay, so event graphs. Okay, the basic form, which we've already covered, is the nodes are an event, which is the state transition. The arc is the scheduling of another event, typically sometime later. And the way that the event list operates, as at least most of you have seen in that first arrival process model that was implemented, that the event list sort of simply processes the next scheduled event. Now, the thing to remember, one of the reasons for doing it by hand was that using only scheduling edges, the only way that an event can come off the event list is for it to bubble up to the top and the event list to take it off. That's so far the only way, but there's another way, and that's something called the canceling edge. We'll talk about that in a second, and just so a little use case for it. The second addition is going to be parameters on the edges. So as you've seen in the implementing the arrival process, that each event corresponds to a method in either SimKit or DeskPy. The convention is a little bit different. In SimKit, the convention is you have the name of the event, but the name of the method is the word do in front of it. Whereas in the Python version, the name of the method is the name of the event except lowercase. Why? Because Python likes lowercase. So those of you who remember that. And so even for those Python users, even though I code Python with a Java accent, I try to kind of regardless of what I'm programming in, as I might have mentioned last quarter, it's important to, as much as possible, use the idioms and the conventions in whatever language you're using. Just like when you speak a language, there are certain ways of doing things, ways of expressing that may be technically correct, but just aren't quite right. An example of that is the difference between Java conventions of naming and Python conventions of naming. So in Java, the convention is camel case. In Python, the convention is everything variable-wise is lowercase with underscores. In Java, you don't use underscores typically, except for certain static variables. So those are just the conventions. both of those are completely allowed. You can write camel case for variables in Python. You can write all lowercase with underscores in Java. And the most that'll happen is maybe the IDE will complain that you're kind of acting weird. But that's kind of what it is. So the next and really penultimate piece that we're going to add to it, which I'll do today, are these parameters on edges. So, okay, why was I mentioning the relationship between event graphs and either Python or the Java SymKit link? Because if an event translates to a method, then methods can have arguments. And guess what? Events can have arguments. Okay, but how do you deal with it? If a method has an argument, then you need to pass that argument to the method when you invoke it. So when an event has an argument, how do you get that? How do you get the parameter into that argument? And the answer is to put the parameter on the edge. So the edge is kind of, you can, as long as you don't go too far with the metaphor, the scheduling edge is like invoking the method, except you're not really. But like invoking a method, if it needs a parameter, you need to give it a parameter. And so you put it on the edge. And we'll see an example. That's a very simple example, but albeit a useful one. And then a use case for that, and I also have the code for that just to illustrate that, because there's a little sort of issue with the upper bound on that, which isn't so obvious. And then really the application of that is going to be just a simple little inventory model in which it becomes very useful to have these parameters on the edges. Okay, so okay, so here's how the canceling edge is represented. A scheduling edge is a solid arrow. A canceling edge is a dashed arrow. Like a scheduling edge, it has a Boolean condition on it, but unlike a scheduling edge, it does not have a delay on it. So a canceling edge, it has no delay, so that when it's executed, it executes immediately. So now what does it mean to, what does that mean? So this, right or one, okay, yeah. So this, whenever you see this, whenever you see the dashed line, the dashed arrow, what it means is that when event A occurs, then the Boolean condition is checked. And the Boolean condition is typically some function of the state. And if it's not there, then it's always true. So that's kind of the inverse of computer program conventions. So in computer program conventions, the default value of a Boolean is false, but in event graphs, the default value of a Boolean is true. So it's not there, it's true. So if that's true, if the condition is true, then it looks through the event list for previously scheduled, in this case, event B. In other words, the event that's at the tip of the arrow is the event that you're looking for. And what it does is it finds the earliest occurrence of a previously scheduled event, and it yanks it off the event list. So that's the only other way that an event can be removed from the event list is if it gets removed through a canceling edge. If there are more than one on the event list, only the earliest scheduled one will be removed. If there are multiple events scheduled at exactly the same time, it's arbitrary which one gets removed. But in any event, only one gets removed. That's important to understand. Okay, so the only two ways that an event can be removed from the event list is if it gets executed, which means its time has come and it gets processed, or if it gets previously canceled. So here's a simple use case for this. So we've seen the arrival process, and the arrival process, I don't know if this happens to you, but actually it still sometimes happens to me when I'm kind of preparing some of these examples. That when you ran it, it just kind of went wild. It never stopped. Did that happen at some point? If you forget to put the stop at time on the schedule or on the event list, it'll just keep running forever. And sometimes that happens and you have to kind of just exit out. But what if you wanted to stop the arrivals at some predetermined amount of time? Okay, when might that be useful? Well, let's say you're modeling a retail facility that does not operate 24/7, like Denny's or something. I was wondering, I noticed that Denny's has a lock on the door. What for? Anyway, okay. So we open it up at 8. You close at 7, and how do these facilities typically operate? Well, when 7 comes around, a lot of times there's still customers who want to kind of come in. So like in some places, what they'll do is they'll lock the door so that nobody else can come in, but they're not going to lock in the customers that are already there. So they let the people out. In other words, they basically shut off the arrival process at a particular time. So you might say, well, what if we put a condition? We could try to put a condition, and it could be done using a condition. As I said, the canceling edges are not absolutely necessary. Or you could say, well, but here's the thing. How many customers have arrived at this closing time? Do we know that? We don't. So a condition based on the number of arrivals isn't going to work for this particular thing. Now, if we're running our model for, let's run it for 1,000 customers, then that's something we could easily put a condition on for that. But for this, okay, so here's an approach, not the only one, but schedule a stop event. You can call it stop or stop arrivals, whatever. And when that event occurs, notice it has a canceling edge for the arrival event, so that when that stop event occurs, it will cancel that arrival event, which means that since this arrival event will not occur, the next one and all subsequent ones won't at all. And that's yet for doing things like this is yet another reason why for something like an arrival process, you want to do them one at a time instead of trying to put them all on the list at the same time. So if we had 1 million arrivals and we put them all on the event list at the beginning, which we could, but we wanted to stop it at a particular time, then when that time came, we'd have to cancel, maybe 500,000 other ones. Okay, and once I get all of the first computer assignment, I was going to kind of show this, but no, it would reveal the answer to the first one. So, okay, any questions about the, yes? Yeah, there's no condition. Yeah. So it will always stop the arrival. Yeah. So thanks for pointing that out. But the key is, because for the arrival process, there's only one arrival event on the event list at any given time. If you take that off, then it just shuts the whole thing down. Okay, that's a canceling edge. Now let's look at parameters on edges. Okay, and this is the canonical representation, and this is all in the reading as well. But so, and so as you can see, it builds on the basic representation of this relationship. So when event A occurs, if Boolean condition I is true, then event B is scheduled T time units later. But here, with the addition of kind of two pieces. One is event B now has an argument. And I'm calling the argument K. It could be, but think metaphorically like a method. So a method could have 0, 1, 2, 3, as many arguments as you want. So this could be a single argument, or it could be a list of arguments, whatever it is. So within event graphs, we can define that. Now, the way that we specify it in the event graph is by putting the parameter that we're passing to it in a little box on the edge. And I haven't found a better way to represent that. The guy who came up with this, that's the way he decided it should be depicted, and it seems like a reasonable thing. The other thing is something that you probably heard me harangue about a little bit last quarter, which is the difference between the expression that you invoke a method with and the formal argument that's on the method. It's the same relationship here. This argument on the event, it's a formal argument. So in other words, it's like a single variable. It's not an expression. It's just a variable that's going to represent what the value that gets passed in is going to be there. Whereas that's why they're different letters, even though sometimes and in fact in the example you'll see sometimes it's the same letter, but with different syntax. So J is an expression here. That's why it's represented as a different letter. This is an expression. So it could be a single value. It could be a fixed number. It could be a single variable, or it could be any expression involving variables and numbers. Or it could be a string if that's, something that you're. So when event A occurs, if the condition is true, again, the condition always is a gatekeeper on the scheduling of the event, then we schedule event B with a delay of t time units. And again, the default is 0 if it's not there. But when event B occurs, then its argument K is set to the value of the expression J when it was scheduled. I left off the when it was scheduled, but that's implied, but I want to make it explicit. In other words, this is like a time capsule, because this event is typically going to occur in the future. Although in the example I'm going to give it doesn't. But typically, actually, in the second example, time permitting, it will. So this is like a time capsule. In other words, you can create a snapshot of some property of the state of your simulation in the future, when we save in the future. So in other words, when B occurs, if I were to evaluate this expression at some later time, it might have a completely different value. But that's not what I want. What I want to know is when this event was scheduled, what was the value of that expression? And this allows you to do that. Okay, so now here's a cute little thing that you can do. And that is the guy who came up with this was back in the early 80s, is when these were first invented. And he was very much a minimalist. So he didn't want. So one of the things that are not included in event graph methodology is a for loop. In other words, you can't literally write for, or do, or any of those things. But we can actually use the language of events to write a for loop like this, and this is how it goes. So remember, we would start with a run event, and so using the zero-based stuff, which we blame the folks at Bell Labs for the C language for, because it saved them an operation. So run now will schedule in what I'm calling it init, that's just, you can call it anything you want, but unlike run, this is just an arbitrary name. So run will schedule an init, passing it the value 0. So when init occurs with value 0, what it will do is it's going to check its condition. So now what M is M is going to be our parameter. So M is going to be the number of times I want this event to be executed. So the number of inits, basically. And the condition is that if this argument I is less than that number -1, strictly less than that -1, then I'm going to schedule another init immediately and pass it the argument I +1. So what's going to happen is that first, run's going to happen. It's going to schedule init with a delay of, all this is delay of 0. This is not like an arrival process. This is all happening immediately. So init 0 will occur. So, let's just sort of try to do it in our heads, say with M is equal to 2. So, let's make it 3 just to make it interesting. Okay, 3. So init 0 will occur. Bless you. So M -1 is 2. Is 0 less than 2? Yes, it will schedule now I +1. So 0 + 1 is 1. So we'll have an init 0. Bless you. So we'll have an init 0, and it'll schedule an init 1. Okay, and once you're done scheduling, that's sort of it. Then init 1 will occur. So now we have an init 1. Now M is 3. 3 - 1 is 2. Is 1 less than 2? Yes, so it will schedule an init 2. And then init 2 is going to happen. Now, M is 3. 3 - 1 is 2. Is 2 less than 2? No, so it doesn't. So we have scheduled 3 of these init events. Okay, so why do this? Well, there are certain situations where I want to have a certain number of a particular event on the event list at one time. So here, this is what that looks like. Here's how I could use that. Supposing I have some event, I'll call it A, and I want M instances of that on the event list at time 0. And so because init, every time init occurs, it's going to schedule this A guy. So as soon as this is done finishing its loop, then there are going to be that many of these instances here. And if each time it schedules, there's a delay, then these A's will just pile up on the event list. Now, even if they don't, and I'm going to sort of peek ahead a little bit here. Actually, when you do something like this, you put in what is the final piece of all this, which is a priority. So in this case, what we want to do is we actually want to schedule this with a slightly higher priority. We'll get into, we'll delve into priority stuff a little bit later. But just to illustrate, if you, oops. Bless you. Okay. Okay. So if you pull, if you do git remote pull, okay, this is for the JavaVoc on the my class code, you will see that actually I have implemented this this for loop here. And so it has a parameter. Parameters are private. State variables are protected, so it just there were unfortunately the way NetBeans does the encapsulation is that it'll kind of, even if you write protected, it'll sometimes convert it. Yeah, question.
Right.
Oh, I do. Thought I was sharing it. Yes. I am sharing my NetBeans, and it is not showing up. Crying out loud. This is infuriating. Let's try this. No. There, okay. You see it? Okay. All right. Okay, yeah, so one parameters are private, have setters, getters, the whole thing. We have a 0 argument constructor and one with our parameter in it. But here is the guts of the thing. So we have our in SimKit, it's do run, and it schedules a init with a delay of 0. And this is the high priority, which you can ignore that for now. But the way that you put an argument on is just the last piece of the wait delay statement. Because why? Because it's wait delay was implemented as a varargs. Remember varargs with the 3 dots? So we can just put the argument on at the end. That will schedule our init. Here's the condition, I less than the number -1. We schedule another init, passing it I plus 1. And so here in the run piece, I just instantiate one. Let's do 5 because the computer doesn't mind. And in SimKit, at least if I print the a sim entity base, then it'll show me the parameters. If I set verbose, I do a reset start simulation. If I run that, and here's the thing is that, again, assuming that the implementation is correct, which it actually is, but the arbiter of whether how a particular event graph is going to behave is that if you correctly implement it in SimKit or DeskPy and run it, then you'll see what's correct. So in this, we have, okay, there's the run. Run occurs, it schedules an init, and then notice the argument is kind of listed in the verbose event list. And so now here's init 0. That schedules an init 1. Okay, what did we have? We had 5, so 2, 3, 4. So just like the 0 indexed array, if I have 5 of the things, they go 0 through 4. Okay, why? It's insane, but you've got to deal with it. The other thing is that notice these little numbers in square brackets to the left of the verbose thing. What are those about? Those are counting the number of times each particular event occurs. So the event list keeps track of all that. So run event happened once. So here's the first init, second one, third, fourth, fifth. Okay, and for those who are just for those who are using Python, this is also implemented in Python, except that I have not pulled it. So this is how, just FYI, if we do a git pull, hopefully it will update my files here. And then in Now that my arrival process is still kind of, just a skeleton. But here's the for loop in Despite. Same thing. Okay, subclassing sim entity base. Here's the constructor. Pass it, unfortunately, Python does not support overloading. So in Java, we could overload the constructor, have a 0 argument and one with the parameters. Can't do that in Python. Python, you just get one constructor, that's it. Calling the super. Basically, here's the other thing. If I pass it a bad parameter I'll get into this more as we kind of go into it. But just as in Java, we want to throw an exception if we have an illegal argument. In Python, we would raise what's called a value error. And so if I give a bad number, but here's the guts of it. So here's the run event. It's going to schedule my init. Now in Python, in the Python one, the priorities are used as a keyword. So the keyword is priority. And so keyword priority high. And again, we'll go into that sort of later. We schedule an init, passing it 0, same deal as before. And so if I is less than the number -1, we're going to schedule another init. And so in the run package, just have a little test for it. So here we're going to do 5 of them. So we set verbose to be true. And then just FYI, and unfortunately for the Python users, I think I forgot to tell you to import event list from SimKit base. So that caused some confusion. But anyway, once that's in, we set verbose to true, we reset, we start simulation. And when we run that, we pretty much get the same deal as before. So if we look, we see there's the run. It schedules the first init. There's the first init, schedules the next one, et cetera, et cetera, et cetera. And at the end, there are 5. And just like in SimKit, the square brackets count the number of occurrences of each event. Okay, so now back to our amazing. Okay, so that's okay, that's his. You can't see what I'm seeing. What I'm seeing is they give me a couple of places where it is listed, and anyway. Okay, so all right, so here's an application of parameters on an edges that's a little more straightforward. Okay, so it's what's called a periodic review inventory model. Is anybody familiar with that term? And I can speak completely freely. Okay, so for whatever reason, and you may have to believe it or not, this actually is one of the policies that are used in certain circumstances. So just looking at one item, and basically you only check it periodically. Why? Usually because this is one of hundreds of thousands of other things. So if you just don't have, and for whatever reason. And the idea is that when the level, your inventory level falls below a certain amount, and that's historically called little s, then you place an order that would bring your net up to a big S if it arrived immediately. So if it were to arrive immediately, it would, it's in a way, it's like kind of filling up your gas tank. So supposing my rule is every Monday at 8 a.m., if my gas tank is below a quarter, if my gas tank is below a quarter full, then I will fill it up to whatever it is. Now, the difference here is that when I place the order, it's only going to arrive after a certain amount of time. It's called lead time. I'm sure you're familiar with that term. Okay. Now, on top of that, we have, so this facility, we have customers that are going to kind of arrive. Now, unlike the queuing thing, they show up, we can actually serve them right away. We could add a queue to this, but it would just complicate things. So they arrive at various intervals, though, according to some arrival-like process. But the difference is now each customer has a random number of items that they want. And so you can either give them those items, or if you're out, then it's going to be back ordered. And that's an assumption. So it's like if you're in like a monopoly-like situation. So if you have customers that will only accept Apple products, and you're the only store in town, and they're out of the particular MacBook that you want, then you'll say, okay, well, I want to buy it anyway, but they'll back order it when it comes in, they'll give it to me. Whereas if it's like a PC, I'll just kind of go down the block and get another one. So that's some of the evils of monopolies. And I'm a Mac user myself, but it's like I'm not religious about it. Anyway, okay. So here's sort of a picture of how that works. All right. So let's say here we start, and so here are we aren't representing the particular. So let's just sort of assume that our inventory stock is just kind of going down at more or less a constant rate. In actuality, it'll be at a somewhat random rate. And so here's our order up to amount. So this would be like our full tank, and this is our trigger point. So for me, it would be like a quarter of a tank, something like that. And in between, we did, so here are review periods. So let's, in this particular case, we start here. Here's our first review period. We check, is our inventory level below our trigger point? The answer is no, so we don't do anything. Then a review period later, now when we review it, we are below. And so we place an order for this amount. Now that orders, but as we're waiting for the order, we still get demand. So now customers are still demanding our stuff. In fact, here we actually go into a back order situation where they want it, but in other words, this is representing inventory position, which is how much we have on hand minus the back order. So when we go negative here, you can't give a customer a negative thing. That's a back order. So we say, okay, we owe you one. So here we might owe them 10. But then finally the order arrives. And so what we do is we fill the back orders, and then we put the rest in stock. And so now our inventory position is here, or actually our on-hand amount is here, and we continue like that. Whereas when we notice that when we place the order, our net inventory, which was how much we had on hand minus the back order plus how much we had on order, was actually up to here. Okay, so you see how that works? And you may be wondering why do it this way, just put that that's not so much the issue, but let's model this. Okay. So, and it even has a name. The name is periodic review little s big S model. This is one of the standard simple models. Okay, so let's look at our parameters here. So we have the time between demands, and that's going to be, that's kind of like our arrival process. But the difference is now we're going to have a sequence of the number of items demanded. In practice, as you've seen in the arrival process, we're going to represent this with a continuous random variable that's ideally positive, like an exponential. And this is going to be a discrete number. So this is often represented as a discrete probability distribution. And in fact, in the models that I'm writing for NAVSUP, that's exactly how it's done. So they have demands in the simulation. The demand will generate a discrete number, and then that's how many that they want. So now, what's another parameter? The lead time. Remember, when we place an order, we're going to get it sometime later. I was rather shocked that when I started working for them, that some of their lead time is like ridiculous. But when you order something like an airplane, it takes a little while to make them. What was a little more shocking was how long it took them to even order the damn thing. But that was sort of enough. Anyway, but that's our lead time. And then now for this model, this would be the time between reviews. Again, now this is now something which is more kind of a decision variable we can manipulate. Now we want to know how much we have on hand initially, so we'll make that a parameter. And then these two values, our order up to amount and our trigger quantity, those are also parameters in the model, but like the time between reviews, those are also decision variables. Those are things that we could typically run the model with different values to see which one gives us the best type of metric. Bless you. Okay, so now what about state variables? Well, one obvious one is how much do we have on hand? So this is how much we have on hand, and it's initially going to be that parameter I0. Another amount would be the amount that we have on back order. Let's assume that we initially have some on hand, and that we don't have any on back order. We could examine that assumption, but let's start there. Turns out that the total amount on order is something that we would be interested in, as well as the number of items that are ordered. And then this is actually not the word no, it's the total number of orders, because that's, why worry about some of these? Because if we're doing a cost model, then every time we have to create an order, that's going to cost us something. Why? Because somebody's got to kind of do that, and we got to pay them. Okay, and then just as a thing, either we're going to have some on hand or a back order, or maybe maybe both, but only one of these is going to be zero. So just like the number in the queue and the number of available servers, only one of those is going to be zero. If we have available servers, then we're not going to have anybody in the queue. And if somebody's in the queue, that means we can't have any available servers. There's a similar relationship between having an amount on hand and the amount that is there. So here's the event graph. Now, as we can see that there's like kind of a little arrival process going on here. I'm calling it a demand because it's not so much an arrival. The demand is a more descriptive one, and that gets scheduled from run with our inter-arrival time at Q sub A. Our run initialized all of our state variables as usual. And then run also schedules the review. Well, I'm calling it a review, which also, like an arrival process, has a time between it of our time between reviews. So these are kind of two arrival process-like things. Let's see, I'm not going to go into the details of the state transitions, because the key piece here is that when we place a review, here's the criterion. So this is our total inventory position, is how much we have on hand, minus our back orders, plus the total amount that we have on order. Okay, why worry about it that way? Because supposing we place an order for 100 and we're still waiting for it, and then we get another review, and if we don't take that into consideration, we might order another 200. And then Murphy's Law says they're both going to come in on the same day. We have no room to put anything. Okay, so the condition keeps that into account. And then this says this is how much we actually order. So our order up to amount minus this quantity, minus that net position. And that is what gets scheduled to the place order event, which I'm now just going to call it A for the amount. And you see, each time, whenever I do a review, this quantity is going to be different. I don't know what that is beforehand. I don't know what that's going to be until I actually place the review. So when I place the order event will now schedule an order for an amount A, which is the argument that was passed. Then notice state transition. So the total amount is now A more than it was before. The number, and then I have one more order that I've been placed. So here's where I'm kind of keeping track of some of the bookkeeping on that. My delay is my lead time. Sometime later, my order arrives. When that arrives, I subtract that quantity from my total. And if I have more than one in progress that I'm waiting for, then I want to make sure to subtract the right one. The other thing is that just due to circumstances, it may be that an order I place earlier will arrive later. So when this order arrives, it will have this particular instance of this will have the quantity that was present when it was placed. So this is a non-trivial use of passing parameters. This is where passing parameters is important, because this event needs to know how many were in the order. And because there could be more than one order, whenever this occurs, I need to make sure that this bookkeeping is done correctly. Okay, so that is, again, finally, come on, stop sharing. All right, question, yes.
So assignment being written, assignment being out, but didn't see the handout at the time.
Ah, okay, that was my bad, so I will have to fix that. I'll fix that as soon as I get back to my office. Thank you. So I was pointed out that the assignment 2 has been posted, but there's no handout. That was a leftover from the class I was giving for psychics.